Thanks. I'll begin. Heavenly Father, we just thank you that you're an awesome God, and we know that our righteousness is like filthy rags, but we're thankful that you came to earth and died for sins, and if we're willing to accept you in our heart, that we can have your righteousness instead of our own, Lord, and we thank you for that. Just pray you'd just bless this class and just give us insight as to what we're doing, Lord, and help students ask good questions as they think of them. In your name I pray, Lord Jesus. Amen. All right, so first order of business here is a correction. One of you was asking about your notes and you're having trouble understanding something, and there's a good reason for that. It was wrong. On the demand of one of you guys, I used E sub t, and we were trying to calculate what happens when you take a matrix, m by n matrix, and you multiply it by the tth standard basis element, right? So this would be an n by 1, right? And so I wrote something different on the board last time. I think I inadvertently changed that I to a t. I think I had this, but with that being a t, and that's just not right. So what happens here when we multiply a, I'm skipping a step here. This is what? This is a formula for Eij, right? We proved that any matrix is the sum of Aij, Eij. And then we also saw that this Eij can be broken up into a product of the ith column vector times the transpose of the jth column vector, like so. And then this guy, well, that gives me the Kronecker delta jt. What that does is it kills this sum over j. It just leaves us with the case j equals to t. So j equals to t, which doesn't do anything to this ei. And that's where I was wrong last time. I somehow got it in my head that that should be switched to an E sub t, which is just nonsense. It just survives, it rides along, here it is, right? And that's good because that's what we need. Because if you look at this, this is the sum, what is this? This is A1t E1 plus plus A mt em, right? Which is exactly that over there, right? Like the first term is A1t zeros, and then so forth until we get to zeros all the way to A mt, which is that. Any questions about this? Okay. So last time I started talking about the concept of the identity matrix, right? And what it does for us. Let me just define it again, make sure we're all on the same page. Definition, I sub n is an element of Rn by n with In, the ijth component of that is just equal to Kronecker delta ij. So this is the so-called n by n identity matrix. Now, in particular contexts, we don't actually bother writing the sub n. So for example, we might say I2 is just equal to 1, 0. I mean, this is I2, but you might just call that I if there was no danger of confusion. And then you could try taking this identity matrix and multiplying it by something. Let's say here, 1, 0, 0, 1 times A, B, C, D. What happens? So we have A times 1 plus C times 0. This one gives me 0 times A plus 1 times C. 1 times B plus 0 times D. 0 times B plus 1 times D, matrix multiplication. Right? Anyway, I didn't need to write all that out. You guys know what it is. It goes A, B, C, D is what I get there. So in fact, there's a theorem that if we take the identity matrix times A, we'll get A. And that's the same as if we take A times the identity matrix. The identity matrix multiplied on the left or the right of any appropriately sized matrix just gives you back the matrix again. So it behaves like the number 1. we have a proposition, which I didn't do last time, but I'll do this time. 2.4.4. And it says that if we have B and C square matrices, all right, and A square matrix, right, with, if we have AB equals to BA equals to I, and AC equals to CA equals to I, then here's the punchline. B has to be equal to C. Okay, so how do we prove this? This is really just plain old basic algebra. So if we know that AB is equal to I, and that's equal to what? AC, what's that tell us? AB is equal to AC, right? Then what do? How about multiply by B on the left? That gives us what? So that gives us BAB is equal to BAC. Right? So then what? Well, A is not the identity matrix. That is not true. I mean, it could be, but it doesn't have to be. BA is the identity matrix, right? That's given to BI. Oh, and we got that on both sides, don't we? So this gives us IB equals to IC, which implies that B equals to C. This theorem we could prove by explicit, index calculations. I have one of these in the notes, in fact. The proof that the identity matrix times a matrix, it gives you back the matrix again. Okay, so there B equals C. Woohoo! There it is. And so that is why we do, definition, if A is n by n, and there exists B in our n by n, such that AB equals to I equals to BA, then A inverse is equal to B, and we say A is invertible. Not every matrix is invertible. Some are, some aren't. All right? If a matrix is invertible, it's pretty nice to work with. Here's a theorem that kind of collects our basic ideas, concepts, conclusions, observations, whatever you want to say, about invertible matrices. So suppose we've got A, B, square matrices, both invertible. All right. And suppose we have Z and W m by n matrices. Oh, I'm sorry, other way around, n by m, like nanu nanu times mommy. And C, a scalar, non-zero, all right? Then here's some things we know. We have the sock shoes property again. AB inverse is equal to B inverse A inverse. Number 2, if we want the inverse of a scalar multiple of a matrix, it's simply 1 over the scalar times A inverse. Or you might say C inverse A inverse if we don't like to write 1 over C for C inverse. What would the context there be? Now I'm pretty open-minded. I don't much care if you say 1/2. Like suppose we're working in Z5. What's the inverse, multiplicative inverse of 2 in Z5? Well, it's 3. Right? So in Z mod 5, 1/2 is 3. So in that kind of context, some professors insist that you don't write 1 over 2, that instead you write 2 inverse for the multiplicative inverse there. So, you know, there are some contexts where you'd really just want to write that instead. But certainly for, you know, complex number, real number, rational number, we write 1 over C. 1 over C for the multiplicative inverse of a number, right? 3, XA equals to YA implies X equals to Y. 4, AZ equals to AW implies what? Z equals to W. I'm not entirely sure. I may have to back it up here a second. Does that make sense? X is what? N by Z and W are... Oh, I didn't say where X and Y were, did I? What? Oops. What about X and Y? Does Z and W make sense? You notice that this is N by N, right? Times N by M. That's good. That multiplication at least is the right dimensions, right? So for the XA, YA to make sense, what size do X and Y have to be? Not N by M, but M by N, for example. Then we'd be having the right dimension matching to make the multiplication make sense. 5, the transpose, the inverse of the transpose, all right, is actually equal to the transpose of the inverse. So it doesn't matter whether you transpose the matrix first and then invert it, or invert it first and transpose. Either way, you get the same matrix. Those are equal. And then 6, what happens if you take the inverse of the inverse? We get the matrix back again. Now, so let's see, what's this called? This is right cancellation. What's this? This is, I would probably call this left cancellation of A. So let's, how about AB inverse? What would the proof be that that works? I mean, any of these are fairly simple to prove. I'll look at one. So consider that if we have AB, right, times B inverse A inverse, what happens? By associativity of matrix multiplication, right? And so that's A inverse, right? Definition of B inverse. And then that is AA inverse, since AI is equal to A. That's a theorem. And then this is I. Also, if I look at B inverse A inverse times AB, that also works out to I, right? By a similar calculation. Therefore, AB inverse is equal to B inverse A inverse. So there's the proof of 1. Now, let me just take a step back for a second here. What if you wanted to derive that formula? How would you derive it? That's in some sense, a higher calling. You know, I mean, I pulled it from the thin air, right? I just wrote it down, and then I plugged it in and showed you it worked. But how would you actually find that formula, the sock shoes formula? So what you're looking for, in principle, is you got AB times C. You want that to be equal to I, right? And you want C times AB also to be equal to I. So you have to solve those equations for C. That should give you the formula for the inverse, right? So how do you solve for C? If you multiply by A inverse, on the left, we get A inverse ABC is equal to A inverse times I, right? Which gives us what? That gives us IBC is equal to A inverse. So in other words, BC is equal to A inverse. Then what? Multiply by B inverse. On the left again, what does that tell us? We get B inverse. BC is equal to B inverse A inverse. But B inverse B is the identity matrix, right? Therefore, C is equal to B inverse A inverse is a pretty good guess. Now that does not prove, right? That does not prove that C is equal to the product of B inverse A inverse. The proof is up in black. Because at this point in the course, I have to show that it satisfies, you know, when I left or right multiply it by AB, I get back to that identity matrix, and that's what's written in black above shows. But this shows you how you might actually find the formula B inverse A inverse, how you might derive it, right? It's not too mystical, really. You just go solve for it, assuming it's there. Once you find it's there, you need to show it works. All right, let's do one other proof here, and then I'm going to go on. Let's prove number 4. How would you do that? So we suppose that AZ is equal to AW. How are you going to get Z equals to W? What do you do? Multiply by what? Multiply by A inverse, right, on the left. And that gives us A inverse, AZ is equal to A inverse, AW, which implies that IZ is equal to IW, which implies that Z is equal to W. That's it. I mean, we could look at the proof of 5 if you guys would like. Let me do that. So the claim is that A transpose inverse, right, is equal to A inverse transpose. So what do I need to do? I need to show, my goal is to show that A transpose, right, times A inverse transpose is equal to I, and A inverse transpose times A transpose is equal to I. Now, when you write something like this at the start of the proof, it's very, very important that you supply extra comments so that I don't think you're assuming the point, right? So I would say something like, our goal is to show these, right? So what I'm going to do is I'm going to look at A transpose times A inverse transpose. All right? I'm going to look at that. And how can I get rid of transposes? Take the transpose. Yeah, I heard that. I heard that. So take the transpose of that. What happens then? Sock shoes, right? So this is A inverse transpose transpose times A transpose transpose by sock shoes. But what are these? This is what? This is A inverse, and that's A, because the transpose of the transpose, right? M transpose transpose is equal to M, right, for all M. Transpose of the transpose back where you start again. But what's A inverse A? That's I. So thus, A transpose times A inverse transpose is equal to I. Excuse me, that all transpose is equal to I. Then what do I do? It's served us well so far. How about we take the transpose again? Right? Thus, transposing star yields what? A transpose times A inverse transpose is equal to I transpose. But what's I transpose? Right, I. The identity matrix is symmetric. So there you go. And then that at this point we have shown, so we've established one. And the proof of 2 is similar. You just start with A inverse transpose times A transpose, transpose it, use the fact that it's the inverse, transpose back to get the other. If you don't have this idea of using sock shoes, I have gotten very confused about this in the past myself. Like this one will sneak up on you if you don't have the, if you don't do like I just did here, and you just try to prove it, it's bad. It's a bad one. It's a bad seed. All right, anyway, there you go, inverses. I gave you the formula for a 2 by 2 inverse last time, right? So what do we say? I mean, so there's some low-hanging fruit we can pick here already. So what if we have we're going to learn that we can write systems of equations. So we'll soon learn that a system of linear equations can be written AV equals to B, where A is a matrix, V is a vector of unknowns, B is a so-called inhomogeneous term. If A inverse exists, and in particular that means we're assuming what? A is n by n, that it's square. In other words, that you have as many equations as you have unknowns. Then what can you do? If we look at AV equals to B, can we solve for V? V is the unknown. Can we solve for it? Yeah. easily solved. Because A inverse AV is equal to A inverse times B. Right? So that tells me that IV is equal to A inverse B. So therefore, V is A inverse B. So in the case that we have n equations and unknowns, and the matrix of coefficients is invertible, we get a unique solution. What's interesting is that often it's not the case that that happens. And it's very much tied to a departure from 3 and 4. Like you can have matrices, right, such that AX is equal to, it's possible that, certainly possible that X times A is equal to Y times A. It does not imply X equals to Y for A which is not invertible. So if A inverse does not exist for A n by n, then we say A is a singular matrix or non-invertible. All right. Let's see here. Let's think about how to come up with an example. Now, what I'm saying is there exists an x and y such that although xa is equal to ya, it's not the case x is equal to y. Right? For a non-invertible matrix, it could still, of course, be the case that there are x and y such that xa is equal to ya and x is equal to y. I mean, that could happen. Certainly, if you just take x equal to x equal to y, it's going to be true. So the point is that there are counterexamples, right? You don't get cancellation for all. It's not enough to know xa is equal to ya to get x equals to y, all right? Here, how about this? What happens if we look at something like E12? What's that? That's, oh, I'm being dumb. So E12 is what? It's E1, E2 transpose A, right? If I do this E12 times A, what's this equal to? What's E2 transpose A? Remember, this is exactly row 2 of A. So what's E1? Am I doing this? Am I wrong? You guys look uncertain. This is n by 1. This is 1 by n. I think that makes sense. I'm supposing A is square. Let's suppose A is n by n, right? What are we looking at here? We're looking at n by 1, right? And this is 1 by n. So this is also going to be a matrix, right? What's that matrix look like? I'll write it out in the dot dot notation just for you guys. So it's that times row 2 is what? That's A21, A22, dot 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 A2n, right? What does that multiplication give you? That multiplication gives you A21, A22, da da da, A2n in the first row, and then zeros. Ah, phooey. Well, I was thinking of x as being the. No, it's. I mean, this example is not wrong. The question is, what do we do with it? So, can you put in words what just happened? Multiplying on the left by e12 does what to a? It puts row 1. Excuse me. It puts row 2 of a in the first row, right? Of e12a, and it puts zeros elsewhere. That's what it does. Let's see here. So let's see here. What if I had, can you tell me how I could have e12a equal to, say, e13a? How would that be? How could you arrange that to happen? What would this be? This is going to be like, what, that's like row 1 of a? I mean, row 2 of a in the first row, right? And this would be what? This would be row 3, right? And zeros. Yep.
As long as row 2 and row 3 are equal to each other.
Right. Yeah, so if we have row 2 and row 3 of a match, we'll have that these are equal. But is e12 equal to e13? No, certainly not. So here's here's an example. So apparently, if we have all we need, right? All we need is that row 2 of a equals to row 3 of a, and that will allow us to generate a counterexample. So how about this? If we just do, say, 1, 2, 3, 4, 4, 4, 4, 4, 4, if that's my a, right? If that's a, then you notice that this has e12a equal to e13a. And so what can we conclude about that matrix A then? It does not satisfy the what property? It does not satisfy the right cancellation property. So what does that tell us about A? A is what? A is singular. A is not invertible. And you can pretty easily see that if you have any row of a matrix repeated, right, then it's not going to be invertible because this calculation could easily be adapted for other pairs of rows. But anyway, I think I have a simpler example in the notes, showing the failure of cancellation, but there is a way to come to it through some more systematic means, okay? Moving along here. Page 33 in the notes, I have a somewhat careful proof of the laws of exponents for matrices, and, whatever. I don't really, I'm not going to spend class time on that. These same arguments can basically be given to prove the laws of exponents for other algebraic systems. I mean, the question is, what do you mean by laws of exponents? Well, you define them recursively. And with that in mind, you get the following properties, which I'll just state for you guys. I don't think it adds much to the course if I work these out carefully at this point, so let me just state them for you. A to the p, a to the q is a to the p plus q. For p and q in the natural numbers together with 0. 1, 2, we have a to the p raised to the q power is, you guessed it, a to the pq. All right. Again, for p and q, either 0 or natural numbers. And 3, if A inverse exists, then 1 and 2 hold for p and q in the integers. The main question you might have is, what do we mean by like the -2 power of a matrix, right? So like what's a to the minus 2? How's that defined? So by definition, this would actually be a inverse squared, where we define square like we did last time I talked about it recursively. So yeah, it still means a inverse times a inverse and so forth, right? Right. Now, this is not actually that surprising. What gets to be surprising is when you get two matrices involved. What about 2? Less boring. So how about we have a plus b squared. What's that look like? So by definition, that's a plus b times a plus b, right? So what's that? Well, we distribute. What do we get? We get a squared plus, however you want to, ba plus ab plus b squared. And some of you were saying 2ab, and unfortunately, you'd be wrong. Because you see, in matrix multiplication, ab does not have to be equal to ba. So we multiply two matrices because they don't necessarily commute. We don't just put 2ab there. It's ab plus ba. That's what happens. And when you do something like cube, it gets worse, right? So you've got a plus b cubed. Well, that's a plus b times this stuff. And so that gives you an a cubed plus aba, I'll do the a times that, plus a squared b, plus ab squared, plus ba squared, plus b squared a. I lost track of where I was, sorry. These first 4 are from this guy. What I'm doing, so I'm just doing b times a squared, b times ba, which is b squared a, and then we got our bab, and then plus b cubed. All right. Does any of that simplify? I mean, do I have any of the same term? Is there any other ABA? No. Is there any other a squared b? No. Is there any ab squared? No. This is how it is when you look at the cube of a sum of two matrices. Now, on the other hand, if you do have that AB is equal to BA, well then yeah, the binomial theorem is still true for all the usual reasons. You can simplify to 2AB and so forth, and use Pascal's triangle and the rest to simplify for higher powers. Binomial coefficients, all that jazz. All right. So the message I'm trying to get across to you guys is, as you're tackling symbolic problems involving matrix algebra, it's very important to keep track of what's left and what's right. Do not assume things commute unless you have a really solid reason to know that that happens. Because generally speaking, things don't commute in here. Unless we're looking at like aij times bij. That is a component, that's a number. In the underlying ring, those commute, because we're working with a commutative ring with identity. Part of the reason we talk about index calculations is because once we get down to the level of components, things do commute. And so we can shift things around there. All right? For example, in your homework problem, to prove the sock-shoes principle, that AB transpose is B transpose A transpose, you're going to have to get down to the level of components in order to switch the role of A and B. Because you can't assume that B transpose A transpose is A transpose B transpose, because it's not. The matrix multiplication doesn't commute. You have to look at components, get down to the level of components where there you can make the commuting step. Reminder. So A transpose equals to A means A is what? And here I'm supposing A is n by n. A is square. Fill the blanks for me. Yeah, symmetric, antisymmetric, some fun things about, so we have proved that the kth power of a symmetric matrix is symmetric last class with induction, right? Here's another fun example. What if you had A transpose? Does that make sense? Even if A is not square, right? If A is rectangular, suppose this is m by n, how big is the transpose? N by, hey, so that product makes sense even when A is rectangular, which is kind of neat. So that always will in fact produce for you a square matrix, even if the matrix input is rectangular, right? And what else can we say about this product? What happens if we take the transpose of this guy? Sock shoes, right? So this is A transpose, A transpose, which is what? Yeah, which is what? That's back where we started again. So therefore, A transpose is symmetric. Comment. If B transpose is equal to minus B, then B transpose II is equal to minus B II, right? But what does that tell you? BII is equal to minus BII. What's that imply about the ith component of B? It's 0, right? Assuming we're working in a field not of characteristic 2. BII is equal to 0. So what is the ith component of a matrix? So we should talk about this a little bit, right? So if you look at a matrix, you got B11, B22, BNN. What's this called in the matrix? That's the so-called, that's the diagonal of the matrix, right? This is the diagonal. So similar terminology we should talk about a little bit. What happens if I've got a matrix that looks like this? So I've got like B11, B12, BNN, B22, BN, B2N, that's supposed to be 1N, sorry. And so forth and so on, Bn, and so my diagonal's possibly non-zero, but then down here, I've got zeros, all right? All zeros below the diagonal. We say that that matrix is upper triangular. This is an upper triangular matrix. That's my stupid shorthand for triangle. What's a lower triangular matrix? Other way around, right? You could talk about strictly upper triangular. That would have zeros on the diagonal. Strictly lower triangular would have zeros on the diagonal and non-zero below. You could also have a diagonal matrix. What would a diagonal matrix look like? So this would be a diagonal matrix if you got 0 here and 0 here. This would make B diagonal, a diagonal matrix. A diagonal matrix is a matrix which only has non-zero entries on the diagonal. So these triangular matrices and diagonal matrices, these are special kinds of matrices, and they do play a special role in various theorems and so forth in this course. So I should throw out the terminology for you. We could prove, if we had time, theorem, the product of blank is blank. So in this blank, you could put diagonal matrices. Product diagonal matrices. Diagonal matrices is a diagonal matrix. And the same is true if we put upper triangular, or if we put lower triangular, or lower triangular. And you could add the caveat strictly. The product of strictly upper is a strictly upper. A product of strictly lower is strictly lower. All of these things can be efficiently and beautifully proved using index notation. Here, for example, for diagonal, what does it mean for A to be diagonal? In terms of index notation, that means that A is equal to the sum I equals 1 to n of A, I, E, I, right? And B, what does it mean for to be diagonal? That means that's the sum, let's say J equals 1 to n of B, JJ, EJJ. Suppose that these are two diagonal matrices n by n. Multiply them. How's that go? AB equals the sum over I equals 1 to n, and well, I and j, let's get to it, of AII, EII, BJJ, EJJ. But this is matrix multiplication, right? The AIIs, the BIIs, these are numbers. You can pull them out front. And you're just left with the product of EII and EJJ. Which is what? Well, I'll tell you what that is. By our theorems, that is Kronecker delta ij, because the middle, times eij. So that makes I equals to j. So what do we get? We get the sum over I of A, I, B, I, E, I. All in favor say aye. I'm sorry, that's horrible. I was just at a math meeting. It's math meeting humor. But this proof is a little bit better than just a garden variety proof. It actually shows you how to calculate that diagonal. You know, if I have 1, 2, 3, 4, and I multiply it by 5, 6, 7, 8, I don't even need to think about it. If I look at the proof, I know I've got 5, 12, 21, 32, because the product of a diagonal matrix is just the product of the diagonals. When you write something like that, it's assumed that the rest of the entries are 0. Okay. And I have the proof of triangular by triangular in the notes, as exciting as that is. Okay. So, talked about symmetric, we talked about triangular, diagonal. There's another kind of matrix which is kind of pathological, called nilpotent. So that means that n to the k is equal to 0, but n to the k minus 1 is not equal to 0, where n square. That makes n nilpotent degree k. So nilpotent matrices are, again, a special thing that comes up in the classification of matrices. They're kind of neat. For example, if we look at the matrix 0, 1, 0, 0, 0, 1, 0, 0, 0, if we call this n, what's n squared? It's actually that. What's n cubed? Right. So therefore n, nilpotent, what degree? 3, right. The other fun fact I would share with you about nilpotent matrices is that if you take an identity matrix, well, certainly if you take an identity matrix, in fact, if you take an invertible matrix plus a nilpotent matrix, you can prove it's invertible, but let me keep it simple. If we have n degree 2, so n squared equals to 0, n not equal to 0, if you look at I plus n, you can prove that that's invertible. Check it out. If I take I plus n, and I multiply by I minus n, what do I get? Yeah, I get I squared plus in plus ni minus n squared. But in plus ni, oh, I'm sorry, I can't do math. One of those is plus, one of those is minus, right? Which one's minus? The first one's a minus, right? I pull out the minus. I times minus n is minus in. So the cross terms cancel. And n squared is what? 0. So we get I. And you can multiply the opposite order, still get I. So this shows you that for nilpotent degree 2, the identity matrix plus the nilpotent element inverse is in fact equal to I minus n. You can prove that this is actually something, it's kind of a funny thing, but here's a sort of a formal idea. If I have I plus n inverse, what should that be equal to? That's 1 over I plus n, right? And so if you believe in the geometric series, what would the geometric series there tell you if you believed in such a thing? Sorry, I'm actually done. Second here. I would say geometric series suggests this is I minus n plus n squared minus n cubed plus dot 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 dot. Taking, just formally, thinking of it in terms of geometric series and like calculus 2, if you believe in patterns, then that should be the inverse of that. And in fact, if you truncate that at degree k, that will give you the inverse for a nilpotent element of degree k. Now you should actually prove that it works. This is formal nonsense. We haven't talked about series of matrices, and I'm just giving you a man behind the curtain kind of calculation, but that's why that's true. Anyway, I shut up. No, next time, Gaussian elimination. Woohoo! Sorry I didn't get to it today, but you know, I got behind Friday.